very much for the introduction and for enjoyment so far. So I want to talk about detection of epidemics, malware, what have you, from very weak signals. This is joint work with a bunch of people. So I'm going to talk about various pieces of work, and I have various collaborators for this work. Eli, Shai, and Ariel are a Detector, the Israeli Institute of Technology, and Chris, the duty, Mikhail, Michael are duty students. Modi is my colleague at YouTube, he's a security researcher, and Konstantin Karaman is from the organization. So let's get going. So this is a quote it says that 80% of those diagnosed with HIV have experienced one or more following symptoms, usually within the first 4 weeks of initial exposure. Fever, rash, headache, unrest, aches and pains, etc., etc. Look at this list. This is what if you look at any illness, this is symptomatic of so much. If you use this to sort of say this is HIV, the false positive rate is going to be ridiculously high. Okay? This is all you're going to use. However, if you have the following side information, all these people have hemophilia, and they went to the same blood bank. Now this correlation tells you, hey, now you're going to push the false positive rates way down because of the side information. Essentially, what we have said is there's a network effect, a community effect, which can take quote-unquote weak signals and boost it in some manner. So this is a high-level intuition. So let's see what we can do with this idea. So let's look at it, for example, in the context of smartphone malware. Okay? And what you want to do is to potentially detect deviations from normal behavior. It's not clear what normal behavior means, but we'll get to that. You want to somehow detect deviations using some very lightweight type of methods, and then use some sort of network structure to say that this deviation, when viewed over this network, is actually meaningful. Okay. For example, suppose you just look at the number of web connections followed by SMS or something like that which was sent from a collection of smartphones. This is a reason. Well, this is not normal, but you don't want to say this is an abnormal thing or an extremely abnormal thing. Okay. But if you say that, well, all these people who did this are actually sitting together in a room, are people who are dealing with insurance for a large group of people, and they all visit the same website. Again, now it looks suspicious. That's the whole thing. That a community structure essentially tells you a lot about even quote-unquote small, benign-looking deviations. Okay, so this is really the kind of question we are interested in. What would it take to diagnose an epidemic from everyday people? Again, an epidemic here I'm using in a broad sense. It's not just disease. It's a smartphone virus. Something which is spreading on a community or a graph is basically what I'm calling as a stochastic process. So the one slide summary, I guess, of sort of this whole talk is this. You know something about the spreading network, then we can correctly detect the epidemic, even if at the individual node level we can't reliably detect these things. Okay. So let's talk about one model. So the talk is now going to be structured in the following way. The first 2/3 of it is sort of a model and some analytical result. The last part is about a system which I've been involved in with Mohit Tiwari and his group, on trying to use some of these ideas to actually detect Android malware. That's basically the plan of today's talk. The first part is essentially it's a hypothesis testing problem at its core. On a graph, that's basically what it is. So what's the problem? You've got an epidemic problem, an epidemic process. It's a contact process evolving in a graph, which means that there's a node that's infected. In case that's infected, that's a red central node. There's a node that's infected. After a random amount of time, it infects its neighbor, and after a random amount of time, that starts infecting neighbors, and so on spreads. This is the simplest model of something which is spreading. If you're a genie and you could see this, and you see this red set of blips moving forward, then it's very, very clear what exactly this epidemic is. Is disease spread. You can now put more bells and whistles on this model, and you can model various things from disease spread to worm spread on networks and so on. And how do you detect that? Well, the genie sees this red and white nodes. Reality is that you're going to see some sort of symptoms. Symptoms here could be that your heart disk is filling up too much, or in the context of sort of some worm which is spreading, or in the case of the disease, we talked about cough, cold, fever, those kinds of things. But these symptoms have many benign interpretations as well. That's really the interesting thing. So we want to see anomalous behavior and try to see whether there is really an epidemic. Now, the weak signature part. So let's look at a very extreme version of this model. Let's say there's just one node in this graph, okay, which we have viewed. Forget about there's a more complicated graph, but let's just pick one node in this graph. Suppose that it shows anomalies as a Poisson process at rate, meaning that whatever you define, so heart disk spin up or cough or whatever. Okay, there's a Poisson process rate 1. Those are the blue blips. There is just a Poisson stream of quote unquote beeps, alerts, whatever you call it. If there is no epidemic, that's all you're going to see. You're going to see this series of blue impulses at rate 1. In case that there is actually an epidemic, you will see, let's assume that you will see one extra blip in this Poisson stream at some arbitrary point in time. Meaning that when you get infected, you're going to show symptoms. But you're going to show symptoms only at that point and never again. This is an extreme version of sort of a weak signature. So the question is, then from a mathematical point of view, you got this one node, you got a blue series of blips. At some point, somebody might or might not have inserted a red blip. You're colorblind. Can you figure out whether there's a red blip in the stream? Okay. Because that's really what symptoms means. You don't know what the cause is. The blue versus red is basically what we have tagged as due to the cause of this this anomaly. Right? But really, you don't know that. An observer can only see symptoms. So from the symptoms, which is the presence or absence of blip, can you figure out whether there is a red blip? And looking at this, it's pretty much impossible. Why? If you look at a Poisson, let's say even somebody gives you an interval of time t, capital T, and say, look at the number of, look at the blips. I'll tell you that if something happens, it happens only in that interval of time, capital T. If it's a Poisson process at rate 1, what would you expect? You would expect t plus or minus square root t, okay, blips in that interval. And in the case that there's an extra red one, you would expect t plus 1 plus or minus square root t. It is impossible to distinguish statistically. But suppose you look at a network, can we do better? And so what is the network model? So let's come back. Let's build the rest of the network around this. So at each one of these nodes, you see exactly the same thing. You see every node has an independent blue Poisson stream at rate 1. Okay? That is the baseline noise process. If there is no epidemic, that's all there is going to be. In case there is an SI epidemic, what's an SI epidemic? That's exactly what I talked about earlier. A node gets infected. After a random exponential amount of time, it infects its neighbor. After a random exponential amount of time, that infects its uninfected neighbor, and so on. There's a spreading process which is going on this graph. So these are the red blips. So at some point here, this node has gotten infected at this point. And then it infects this node at this point in time. Then this node gets infected at this point in time. This node gets infected at this point in time, and so on. And the time at which it gets infected, it's showing an extra red blip. Now, let's go back to the same question we asked. You are again colorblind, so you are seeing a series of blips in impulses at various nodes. Okay. Question, can you distinguish between these two hypotheses? Hypothesis 1, there is no red tree of blips. It's really a tree of blips because if you look at the causal unwrapping of that, that's really what's happening. There is no red tree of blips on this graph. Hypothesis 2, there is on top of this Poisson base tree, there is tree of red blips. But every node still shows exactly one thing and no more. Okay. can we distinguish between these two? Or in what regime can we distinguish between these? Is the abstract question clear here? Perfect. So I described what an SI epidemic is. So how does the network spread? Is more precisely the following. A node is initially infected. It starts an exponential clock at rate beta on each one of the outgoing edges. When the earliest one of these clocks tick, then that particular node gets infected. And immediately all the clocks gets reset because of the memoryless property of exponential. And there are now a whole bunch of new clocks. Okay? And then somebody else gets infected. And the number of clocks keeps on expanding as the number of nodes gets more and more red ones. The number of exponential random variables start increasing. More and more nodes get infected. It cascades to the next.
And what happens if the A infects B and your model takes into account the fact that B will not infect A?
So it will start an exponential clock, but it doesn't matter. A node which is once infected is infected only once.
Yeah, but doesn't that have an implication for the infection problem because you get more data?
No, it's not going to. As I said, the detection side, you're going to reveal it only the first time you get quote unquote somebody tries to infect you. The second, so equivalently you can say that all those edges, once somebody gets infected and all their neighbors are infected, all the edges are removed as far as the spread is concerned. We can do it. Okay, so this is a standard. It's called the susceptible infected epidemic process. And the question is there an SI process overlaid over a Poisson string, over a graph of Poisson strings? That's the real question. Then let's do a back of the envelope calculation to start off with. Let's look at this nice star-like graph. Okay, it's useful because we can actually sort of build intuition very clearly on it. What's the network? Well, there's a single central hub node. There are spokes. There are totally n nodes in this graph. Each spoke is ordered root n, and there are root n spokes. Okay? So that's basically this graph. There are there's n nodes, root n nodes in each length, and root n spokes. So that's so we'll see what happens here. Suppose I'm just looking at let's just look at one hub. Okay? This is the calculation we started at the beginning. We are looking at suppose you look at a window of time W plus capital T. And all we want to do is to count the loops. Well, the pure noise Poisson process, because it's a rate 1 Poisson, you will see T plus or minus square root T loops. On the other hand, if you have an overlaid epidemic on top of this, only at this node, you're going to see T plus or plus 1 plus or minus square root T. And the question is, can you distinguish between these two hypotheses based on count? And it's with high probability. So again, when I mean distinguish, I'd like somehow the probability of error to go to 0, either type 1 or type 2. That's what I mean by distinguish. Clearly, you cannot do it in this setting. However, now let's do the following. Instead, hey, you know that the graph is size root n, right? The epidemic is spreading at rate 1. Let's say beta equal to 1 for simplicity. It doesn't need to be, but for simplicity, let's do it. So if you think about it, look at any particular spoke from here to here. It's root n hops. So the expected amount of time for the epidemic to, in case you do believe there's an epidemic, the expected amount of time for the edge n nodes to get infected will be order root n. So if indeed you believe that at time 0, quote unquote, the source node was infected, then by time order root n, now most of the nodes will be infected. Not all, because there's some tail probability events, but we ignoring that.
So you're assuming that you have time spent.
Good question. Actually, right now I'm not going to late. I'll come back to this issue. I want to sort of build up. Right now, let's even simplify the binary hypothesis question to the following: is there a Poisson's? There is a global notion of something called time 0. Okay, there is a global notion. There is an. I even tell you that if epidemic spread, it will start from this node. Okay, I even give you that and ask you: is there a tree or not? That is not me. We'll remove those assumptions later, but for now, let's even ask just that straight question. Then, in which case, what happens here? Well, so let me choose a window of time capital T, which is equal to root n, and instead of counting just the number of blips which I see at this one node, I'll just compute the total number of blips over the entire network. What happens? So is the algorithm now, the new algorithm is the following. I don't care about the graph structure. I just look at all the blips I count in the entire network over the time 0 to root n. And is there something that will be done? Well, let's do a cat. Now let's do this calculation and see what happens. If I choose a time root n, the number of alerts, how many blue blips will I see? Well, there are n nodes in the graph, each one being measured for root n amount of time. Right? That's my time window, which means there's n times root n expected number of blips because the baseline is all Poisson array. So I see n to the 1.5 is the number of random alerts. And because of the standard deviation, there will be square root of that. So you'll see n to the 1.5 plus or minus 0.75 blips. On the other hand, if indeed there's an epidemic also spreading, well, you're going to see, of course, the n to the 1.5. You'll see plus a theta n, because they're the red one, there will be an order n amount of red blips, plus or minus 0.75. Of course, this mean is overwhelming this. If I just look at this total count, there is no way I can pull this out. But really, if you go back to COM, we don't care about the mean, we look at signal to, the signal is this, the noise variance is this. Really, the SNR is not this divided by this, it's this divided by this. You have fantastic SNR here, okay? Because all you do is, I know that the baseline expected value is n to the 1.5, I'll just subtract it, okay? Then really all I'm distinguishing is n to the 0.75 versus theta n plus or minus n to the 0.75. It's trivial now to distinguish between these two things, okay? So that's the key thing, that the network is boosting the SNR dramatically here, okay, by just simply counting things. Does it make sense? Is the best you can do? No, in fact you can even boost SNR better. Let's look at the adaptive count. Okay. So now we need to understand a little bit of how epidemics spread. That's why this graph is actually useful. Now I'm going to use finer network structure. We know that if you look at this, because this graph is trivial, along each spoke, for any particular node, there's just one way it can get infected. Okay. If this node is infected, that the red spike is there. The only way it will happen is it goes traverses along and gets here. Which means that if your k hops along a particular edge, okay, the time taken for the expected time when you get infected is equal to k itself. Or if the SI parameter was beta, it's k by beta. But I'll just set the SI parameter equal to 1 for just lack of other calculations. Then it's linear. Okay? So what will I do then? Hey, I know that if there's an epidemic, and as you pointed out, I know when to start looking as well. Okay? So for this node, I will look at times starting from k minus some standard deviation about it, alpha standard deviation about it. I will simply count the number of blips in this window. So now, that's what I will do for this particular node. For this particular node, I will use a different window. I know the expected time it will get infected is root n. So I will look at root n plus or minus root n. Okay? That's what basically what I'm going to do. So for each node, I can define a window for which I'm going to count the number of blips. And then see what happens when I do that counting. Is this adaptive window clear? Okay. So the calculation here is again pretty straightforward for this graph. So I'm going to observe all nodes, but with a sliding window. So it's not a fixed W anymore. For each node, as we discussed, it's a different node. The noise is still a baseline Poisson process. So there are two things to count. One is how much random blips will I count with all these sliding windows. This is a hand-wavy calculation. I can sort of tighten it up, but you can believe this, which is that, well, this window capital T is order root n roughly, which means they're 0.25, okay, n to the 0.25, and then there are n nodes. So roughly, you should see n to the 1.25 number of blips. And if that's what it is, and because of independence and usual Poisson process system, the amount of variance you'll see is n to the 0.67, the square root of 1.2, but half of 1.25. If you take square root of n to the 1.25, then the variance is simply half the exponent, which is 0.675. So in the epidemic plus noise hypothesis, what you are going to see is n to the 1.25 plus or minus theta n. Again, because that's the red, plus theta n, because that's the epidemic test, plus or minus n to the 0.675. You even boost the SNR even more. So this says one more thing. You really don't even need to see the entire network being infected, okay, which is theta n. You need slightly more than 0.675 exponent, which means, which comes to the point, you want to detect early. You don't want to wait till the whole network is infected and figure things out. So really what I need to, going back to this network, this calculation says, I need to take a small ball around the center, okay. How much should that ball be? It should capture more than this value, okay, in terms of the number of nodes. It's still a vanishingly small fraction of the network, because the network has theta n nodes in the whole thing. Okay? So I pick a small ball, say n to the 0, it has n to the 0.68 nodes or something like that, and then my SNR is going to be strong enough, I can figure things out. So this means that to track the frontier of the epidemic, that's what we are doing with adaptive window is simply a way of tracking the frontier of the epidemic. We are tracking the frontier of the epidemic through this K. In this case, we could calculate everything out. And then focus on looking there, simply counting things is going to tell you everything. In spite of the fact that each node is just giving one extra blip, at first sight it looks impossible. But so the spread dynamics helps you a lot in this. So this really the rest of it is now how you build the math around it. But the idea is essentially just this. You take this graph and you can see all these things happening. Now, if you've got a more complicated graph, you've got issues. What do you exactly mean by a frontier? For example, if you take this not to be a star but a grid, you've got many paths by which a node can get infected. You've got first passive percolation happening on this graph. So you need to do sort of inverse problems with activity. That's really what it involves. If you've got that GNP Erdős graph, you've got something happening on tree-like graphs. So you need to do something else. But essentially, the game always is going to be try to understand, track the frontier of the epidemic spread. If you're tracking the frontier, figure out what is the variability you have, or you have certainty in where the frontier is, and look carefully, count number of blips in that area. And that's basically all that needs to be done together.
It seems to say that this is more than just a number of observations. Because he said, I would guess, if you have more observation about the evidence of the detector, you were saying that this is more than.
Yes, okay, let me give you one more. I'll tell you why it's not just that. In fact, if you have too much observations, you're going to get into trouble again. Okay? Why? As you increase your window, your noise is increasing, but your signal isn't. Because you have only one blip. Okay? So it's not that more observations are going to help you. You shouldn't look too much, because all that more observations are going to do is to give you more and more noise.
But on the other hand, exploring, I think, don't seem to add really that many more observations, and yet you're not using the control sequentiality that comes from these additional blips. So what gives us?
The temporal sequentiality is actually encoded in this K. The window size is because of the temporal structure. Okay, so we are indeed using the temporal structure. That's really what is giving here. Okay, that you know that at each, suppose let's look at a different model.
In a very weak sense. Right?
Yeah, in a very weak sense. But that is enough.
And that's enough.
That's enough. I'll state the formal theorem in just a second. We are using it in very weak sense to focus in on where to look. In particular, let me give you this thought experiment. Suppose that a genie told you, if you got infected, you will get infected 1 hour and 1 millisecond from now, and nowhere else. Okay, suppose I give you that fine resolution. Then it's trivial to check epidemics, right? Because I just need to look at each person exactly at the right time. Okay? So the game is, when do you look at each node to figure out whether they're going to get infected? And that's temporal resolution.
And if you were to look at a practical case, for example, walking later, we talked about AIDS, right? Nobody's going to tell you what the network is.
Very good question. So what is it? So really, that's a fantastic question. Here, what is the network giving you? It's telling you when to look at something. Suppose you don't know the graph. Okay? Network is basically giving you correlations on who will get infected over what windows of time. So let's look at a community. Suppose that so say we are sending emails or something to each other, and so some phishing attack is happening. It usually happens in a 1 hour period from which, or in a small amount of time from which the first thing hits a particular community. So the filter should be count all the blips within whatever you define as a community over a triggered by a particular event, which you think is suspicious.
I'm not sure I understand your answer in the context of AIDS.
So in the AIDS, so I would look at people, I would monitor people in the blood bank who go to the same blood bank, for example.
So you're doing epidemic detection only in that very fine. I mean, we're not talking about detecting AIDS within a larger community.
So what you need to do in the larger community, you need to do the same. So this also infection is spreading on a larger community. But you say that I'm not going to look at signals everywhere. I will look at where I know that signals gets boosted. For example, AIDS, going back to just the AIDS detection. I think in 81 or 82 it was actually called the 4H disease. Because of, basically it's a network effect type disease. It was certain communities. So what would you do then? If you knew that, then you would look always, you would put an observatory, quote unquote, on certain networks, on certain communities, but you will not look at them all the time. You would wait for a triggering event in any one of these communities and look at a window of time plus minus in some window. And then that will basically boost, that's what it means here. You have to boost your signal, you have to look temporally triggered by this thing, and graphically triggered by something else.
So once you have the observation, you start going back and observe, is it what you say?
So I'll tell you what we have built in this thing. So right now, you're right. This is such a stylized problem. Mapping it to anything real, there are many hoops to jump through. Okay. So I will talk about one mapping of this to real. Give me another 10 minutes or so. I'll get to that.
And you will tell us how to scale?
I'm going. Still, I haven't even told you what the result is.
Okay.
This is a baby graph on which I wanted to do everything explicitly so that things are clear. Okay. Let me tell you what the mathematical result is in just a second. Okay. But before that, let's talk about what's been done in this kind of work. There's been, I guess, a sudden major interest in sort of network inverse problems over the last decade. Okay. There are sort of multiple streams of work. One is inferring a spread. Is there a spread? Is there a spread or not? One line of work is by Arias Castro, Candace, and Theorem. I'll talk about that in just a minute. Another is with myself and my collaborators. We have been looking at sort of hypothesis testing type various. I'll talk very briefly about what. A second class of problems is rumor source detection. You've got a spread, you want to see where it started from. You already know that there is a spread. It's not noisy, or it's not this, at least at this scale of noise. And you want to figure out where it starts from, so you need to construct trees essentially and find sources of trees. There is a very nice line of work there. Another line of work is to find the network structure and parameters. So you've got an epidemic spreading, can you find the rate of spread? Or can you find the graph itself? Okay. I told you that I got infected now, you got infected slightly later, someone else got infected later. What is the graph this way, or is it that way, or is learning graph structure? So that's again a hard problem, but there's some beautiful work by Netapalli and Sangui. It basically shows that it can be actually posed as a convex problem if you do some tricks, and you can learn the graph there. They formulate the ML as convex problem. So there's various types of research. Again, you can see the dates are all sort of recent. So there's been a sudden interest in graphs plus inverse problems for the last year. So the work by Arias Castro, Candace, and Duran is essentially the following. It's a nice problem. You've got a graph. I've drawn a grid, but that's just for illustration. They don't really assume a grid. You've got a collection of nodes, whether it's a graph or not. And each node reveals one random variable, which is randomly picked Gaussian with mean 0 and variance 1. So everyone has a single sample. There's a collection of sets, K, max cal K, and there's one set K in that. All the nodes in that show a Gaussian mean mu and variance 1. You know that there's one set with that. Can you figure out which set it is? If I tell you this collection of sets, can you find that set which has Gaussian mean mu? Then mu is really, really small. That's the version of this. Sorry? This is a
So this is a single node where it's
single set of nodes. So
but the first line says what?
but first line says every vertex V has an independent Gaussian realization, which is Gaussian 0, 1. In addition, there is except for one set of nodes K.
So in addition to every node having Gaussian, there's a subset of nodes that have another random variable, independent of everything else, but with different parameters. Is that what you said?
Exactly. And they go, that set of nodes, Gaussian is deleted. The original Gaussian is deleted. Everything other than
All right.
V slash K, all are Gaussian 0, 1. K is Gaussian mu 1. Which can you identify which set it is? And so they basically focus on the complex, how the description of K, because if K is arbitrary, it's impossible, it's very hard to figure this out. So they're interested in the complex, how to describe the complexity of this class versus the mean. It's an analysis of that.
What's the structure and script case?
They're interested in sort of the geometric structures, how to use, so these are all embedded in Euclidean space, and that's basically what they're doing. So spatial geometry is what they use to figure this out. So their tests are basically scan statistics. Okay. On the other hand, so another sort of static line of work which I was involved in is the following. You're given a graph on which every node either reveals a bit or you stop the system at some point in time t. At that point in time t, you don't get timestamp information. You get a one-shot information. Did this node show a symptom or not up until now? Think of this a city, okay, and you want to figure out. You sample a small fraction of nodes which show a particular symptom. Okay. Don't know when they went to a doctor or they complained that they're not well, and you want to figure out from this whether there's a spreading process or it's just random noise. I think of this as the allergy versus food problem. You've got 1 million folks in Austin, and you sample log n, which is 1,000 people, who are sort of showing symptoms. Is it because of allergy or the flu, both of which have very similar symptoms and start around the same time? That's the kind of problem that this curve looking at here. And the noise here is of different type. Most nodes don't report anything. Okay? So you don't see a connected component ever to even see. You get log n samples out of n. And you can say that there's a lot of false positives. Say alpha fraction of them adversarially lie, for example. Okay? They basically say, I'm feeling sick too, because not really, just because they want to take off from work that day. So then this is again a different type of hypothesis testing problem. Again, if you don't know the graph fully, or I delete some edges of the graph, or various types of noise models. So that's not what I want to talk about. I want to talk about the dynamic problem. But these are sort of other related things. So let me quickly go through the theory, and then I'll talk about the system side. The model is you got a general graph. Noise per node is Poisson at rate 1. Epidemic process spreads at rate beta. Observations are you got the window type observation we talked about. You're allowed to count the number of blips for node I between Wi and Wi plus Ti. You choose Wi and Ti. And the algorithm input would be a set of nodes S, exactly as what we saw, and a collection of windows. And the algorithm we have been talking about is the count. Simply, if the total count over the observed nodes, over the observed windows exceeds some threshold, then return
An assumption that script S is in a sense like the neighborhood. In other words, that if we know that there's a path within that S, or we put
No.
that as disconnected.
The algorithm, so this doesn't even describe what S or Windows is. I'm just describing a black box. An algorithm, given any S, whether it's disconnected, you choose your favorite S and choose Windows when you want to look at these things. And this algorithm will, the count algorithm essentially counts simply the
No, I
total number
understand,
of
but
bits.
if S is not connected,
Sure,
then-
man.
of course not, but then don't you lose some power in terms of...
Absolutely you lose power.
What you've been arguing, right?
So, let me tell you, I think this is what you're getting to. So, the algorithm basically, our result is a type 1 and type 2 error probabilities asymptotically go to 0 under the following conditions. The first is the signal factor condition. Your S and the windows are such that under the epidemic hypothesis, you capture at least card S to the 1 minus eta number of bits for some E. So you don't need, so this comes back to, so how much power you lose depends on eta. Okay? You may, in particular, if eta equal to 0, you have captured all the power. But you could scale back polynomial. It depends how you're doing this. The noise condition is that, well, your average window size, Ti, these are the Ti's, the average window size scales as S to the 1 minus alpha. That means if the window size is S to, so for example in a grid, alpha is half. Or actually in the spoke network, the alpha is half. So the expected number of random alerts then will scale as you lose at each this average, then the number of nodes you're looking at is card S. So you simply multiply this by card S, and this is the expected number of bits you're going to see over the screen. So we know our basic intuition for our previous calculation said that as long as the number of alerts exceeds the standard deviation, so hopefully square root of this, then all should be good. So which means that 1 minus eta should be larger than 1 minus alpha over 2. It's exactly what this is. The theorem statement says that indeed if this happens, usual concentration of measures on graphs will let you, or on structures, tells you that this kind of thing happens. So I think this sort of, it tells you the trade-offs. It still doesn't tell you what to do for any graph, how to find these sets. Okay? I will go through the calculation for one type of, one particular grid. I mean, I have multiple things in this talk, but I'm not going to get through them. So I need to understand how things spread, which basically comes to something called shape theorems. So the results we use actually is Custon's results on first passive calculation on grids, and speed theorems on random graphs. There are a bunch of things. What we use is recent work by Amidi et al. On Centennial theorems on random graphs. But I'll just stick to sort of shape theorem for grids. So what does shape theorem say? Well, suppose there's a node infected. Sometime later the node gets infected, and so on. So this is how the time dynamic of a spread looks like on a grid. What can you say about this statistically? For example, you could potentially have a collection of red nodes to be looking like this, the ball and such. It's unlikely. You expect sort of nice, sort of ballish shapes. In particular, you'd like to say that the frontier of the epidemic can be tracked between sort of two balls. Is what you'd like to say, and the radius of this is somehow a function of time from which it started. That's the kind of thing you'd like to see. And on trees, what you'd like to see is sort of how far, if you have a root node, what is the depth of depth and density of the frontier. That's sort of the kind of results you'd like to see. And these are well-studied mathematical problems. So, in general, what you could ask for is a general shape theorem. So given any time t, okay, can you find two balls, given that an epidemic started in node I, such that the one ball is within this set and the other ball is outside this set? What can you say about these kinds of things? So the speed condition basically says this means window size is proportional to expected infection. That's basically what it's saying. So what we can show, this particular general speed theorem for this kind of thing is to, my colleagues, the Pramanists and Shaiman or student, Christian, is that indeed you can show these kind of things for any bounded degree graph. It may not be the best constants. To get the best constants, you need to do much. You can do much better. But at least you want this kind of linear thing. If you don't care about the constants, you can, for any bounded degree graphs, you can sort of show this kind of thing. But best, if you have better constants, for example, custom results, you can do way better. It's basically from 0.75 to 0.675, those kinds of things. So what's Custom's theorem? Sorry, I'm going to be sloppy. There's the more formal versions in the previous slide. Essentially, there's a basic shape L0, okay? And the ball can be trapped between t times L0 and t plus or minus some small fudge factor, which is t to the gamma, which is something. And gamma is slightly more than half. You can choose and get things. In fact, the result is very powerful. It's explicit. You get the exponential concentration. You need that for the calculations, and it's not only for dimension 1 to 2D. These results extend in general dimensions. So once you have this kind of sort of shape concentration, what does this say? Say, suppose that an infection started at a particular node, then it tells you what the windows to choose. You start looking at it when this edge crosses the node, and stop looking at it when this edge crosses the node. This basically tells you exactly what to look and how much to look immediately. So I'll skip details, but yes, if you can choose the things as I described in intuition, everything works out, and we can use a sort of master theorem and just show that the parameters can be chosen appropriately to make it. Just here. So I want to talk about two other issues before I move to practice. One is the question you asked. I don't know where it's going to start or when it's going to start. There's a naive way of dealing with this, which is look at assume that the epidemic starts for each blip. Okay? For each blip, you sort of spawn a new algorithm and at every node, and then run these polynomial numbers. So if you look at a polynomial amount of time and the polynomial number of nodes, the number of algorithms you're running is also poly. So it's an ugly algorithm, I admit it. But we can of course, it's basically a source times search. Okay, that's basically what we are doing. And because everything is polynomial and the concentration is exponential, everything works. Mathematically, there isn't a problem. The Chernoff bound basically, Chernoff bound plus union bound things. So it's not really a showstopper. It's not an algorithm which is nice, but it theoretically works. What I think is more interesting is sort of if you have some more nice graphs function, which is the hub watcher. If you have power law graphs, how is intuitively the way infections would spread? It starts somewhere, reaches a hub, and explodes. So what this says is, don't look at hubs, look at one-hop neighbors of hubs. Okay. So you trigger an event by a hub showing an alert. Okay, and then look at all its neighbors to show they all show simultaneous. They all show alerts very close by. Okay, so this is the hub neighbor watcher. Okay, things work out in that kind. So this is much cleaner because it quote unquote not solves but addresses your space-time search. It says I don't know. I'm not trying to find the source. I know that wherever it starts, it hit one of these things, and immediately after that, I'll see something light up neighborhood. Okay. So again, you can. When I say succeed, all these things are in formal sense, type 1 and type 2 error properties both. So that's basically one partial answer. But in general graphs, yeah, it's more tricky to sort of, without sort of just running this brute force search. Okay. So, as you all already brought up, and which I clearly acknowledge, this is a stylized model. It's a far cry from reality. There are like a zillion different problems when you get to reality. You don't know the graph. You don't know what an anomaly means. What do you want to measure? Will people opt in? If you're measuring people, will they actually report? I mean, there are so many dimensions of problems here. It's not clear how to make the next step. So what we are going to talk about now is one application of this. It's still a baby application, but less stylized than the previous. That's about all I can say. So the application is the following. I would like to find whether you are playing a malware version of Angry Birds or a real version of Angry Birds, or whatever else app you have. You've got an Android network. The community here may be that people go to similar app stores, maybe somewhere in some country X, which has some non-Google app store, and tainted versions of games. And so you have some rough notion of communities, and you want to sort of look within the communities to see whether there is bad apps or good apps. Now, how do you even detect bad apps versus good apps? What we are going to do is to just measure function call traits on Android. So on an Android platform, it turns out there are 349 different function calls. So it's a time series, okay, on the OS. So we just take the OS trace, and then from that, what can we do? That's we want to sort of say something is normal, something is abnormal, we have the opt-in issues, and so on. So let me now describe what our setup is, and then come back and talk about what kind of results we get. Yeah, as I said, problems are everywhere. Well outside my domain of expertise, but nevertheless, to get this to work, there are problems. It's not a clean SI model. We don't even know the spread dynamics. We don't know the graph. Nodes may just decide not to report anything, and reporting. So what is the statistical baseline even? So first, let me describe the platform, then describe what signals are, and then talk about it. So my colleagues, Mohit Tiwari and their students, in the following class. On a cluster, there are many instances of TestDroid. TestDroid is an Android emulator, where actual mobile apps can be run, and these apps can be delivered by pre-recorded user inputs. So my colleagues got 270 hours of traces. They got a bunch of students to play various apps and recorded their finger movements, everything, okay, what exactly they're doing. So they've got human simulation. And there's also something called Monkey. It's an Android random input user input generator. It's not as good as real humans because apparently it doesn't stress depth of the app. When you play an app, it's really a free state machine you are exploring. Okay. Humans are way better at exploring state machines more than Monkey. Monkey doesn't explore very well, is what I understand. I mean, this is not what I do, but yeah. So if some things I say here are wrong, pardon. But they got a lot of data. They spent a month or 2 months actually. They spent, I think, 6 months to build that platform, and then a couple of months getting students to do all these things. So this is the data set. Then, on this now, we can build a community. Now this is the simulation side or the emulation side. You can put whatever, you can say there's a graph, and we didn't want to put a graph-based model. We just said there's a community, and the infection occurs over some interval of time. We don't know any finer structure. So our windows are basically just using whatever code structure we have. So a waterfall attack, for example, means you look at a particular community and you know that triggered by an event for the next hour I'm going to look. That is the level of coarseness over here. Okay. Then you want to do community level blip detector. So what is a blip? Next, that's the next piece. So there are 10 different apps that are being played. Wikipedia, the Walmart, Yelp, and Angry Birds, I think, and so on. Each device generates a system call trace, which is 349 function calls chunked into 1 second windows. So look at every second window, you get a histogram of the function calls, and then what each device is generating is a time series of function histograms. From this, you can extract feature vectors. So this is a high dimension, 349 dimension thing. You can do a dimension reduction using the usual methods. I mean, these are all black box things essentially. You can go to, we reduce it to a 10-dimensional thing, and that's basically the basic. it's a 10, and for each second, for each node, there are 10 dimensional vector. Then these vectors need to be fed into some lightweight detector on the phone itself. We call this a local detector. This could be a random forest, it could be some again black box classifier. Which you have to tweak, we build, but it's worth to build that stuff, but it's not quote unquote research. It's not something which we invented. It's finally known methods. So you send it. So the output of each local detector is what we call a grid. So now we have mapped our impulses in this system. So trace is being generated, you're doing a dimension reduction in real time, you're sending it to this local detector in real time, it is saying okay, not okay, okay, not okay. This is the equivalent of our Poisson pulse. So
just the statistics that you're collecting, since this is all collected, to show that it is indeed Poisson.
Actually, I didn't even check that. That's a good question. I'm not sure. First of all, I'm not sure. It will not be because it's discrete time. So it's a job. So it's the baseline noise. I don't know the answer. If I remove the timestamp, that's a good question. I didn't even think of.
I can go back.
We have all of it stored. I will. Now that you ask me, I will try this. So what are the? So now these are the apps. The bad. So each app has a bad app version as well. They steal file, there are steal contacts, steal SMS. There's a whole list of bad types of apps, and they all have different types of things. The table says the different types of apps. Since I have 5 minutes, I'll skip what exactly they are. So we had a wide sort of menu of good things, bad things. 18 different types of local detectors. Basically, through everything we do about what is around in machine learning, local sort of lightweight techniques and systems. And it alerts it raises these alerts. So, given this, can we detect if there is malware in the community? Now we have talked about a particular instance. There are multiple problems here. The local detectors, it turns out, empirically have true and false positive rates about 80%, 20%. So there's about 20% error all the time in these kinds of things. Which means that if you have a reasonable sized community, you're getting like boatloads of blips coming to the system, okay, all the time. A second problem, which is sort of interesting theoretically as well, is the following. People, you said that you are a community. Some of you, whether you believe that you have a malware or you want to take part in malware or not, may decide not to take part of it. Okay. You may say that I don't want to send my signal to some global thing because who knows what it is going to be. Okay. Right? So, just because I say there are n people in a community, it's not clear that actually from a statistical baseline, the noise is from an n% thing. It's an arbitrary thing. Okay. People come in and leave. Okay. They move out. They may decide to censor their signals. They may just decide they'll walk out of the system and not let anybody know. There's these kinds of weird effects going on. So previously, let's look at our sort of beautiful baseline. We had n to the 1.5. Okay, that was the signal. Okay, the over mean of the noise. There was a signal which was n and noise which was smaller than that. But if the n to the 1.5 has uncertainty, you're completely swamped. Okay, so that noise is going to swamp all the randomness noise, and you can't do anything. So you need sort of more fine grain. You need to do something else. And so there's one more trick that we do, which is the following. I'll switch to a stylized problem, and you'll see the connection in a minute. Stylized problem is the following. Suppose you've got n nodes. Okay. Suppose you have 100 nodes. All of them are Gaussian with mean minus. All of them have one real number associated with it. They're all Gaussian mean minus 1, 1. We call it. Or all of them are Gaussian 1, 1. Malware. This is a very, very strong thing. Everybody has malware, everybody is benign. This is just a thought experiment. So let's look at this, and that's all this malware or benign is. Can you distinguish between these two? Of course you can. because you simply, it's this basically the simplest way a hypothesis testing question to be teach at an undergrad level. Okay? It's a binary hypothesis testing question. You've got a vector of 100. It's just this hypothesis. Can you figure it out? Yes. If with 100 samples, you can simply count the number of errors, and the probability of error is something ridiculously small, okay? Because you've got so many independent samples. Good. So if you know the count, there's correlation with the community. Just by counting the errors, it's very easy to figure things out. Fair. I change the problem. There are n nodes unknown. Okay, this is the problem. Not 100, but I don't know how many nodes. I give you 100 samples of alerts. Okay, let me go back. What is the test here at each node? When I say alert, the hypothesis test threshold is 0. Okay? If the signal is above 0, call it an alert. If the signal is below a 0, call it no alert. Right? Just to make that. That's the because this hypothesis I'm assuming is it's a Bayesian setting, both are equally likely. Then all I need to do is count the number of alerts here, and that's what I mean by the probability of errors. So the alert is clear. The local detector is basically just a binary hypothesis testing at level 0. What if I tell you that I give you 100 alerts, or I give you 95 alerts? You see that there are 95 alerts, but I don't tell you how many people have actually taken part in this. Totally. So the question again is the following. It's exactly the same underlying thing, only I don't know that what the baseline is. The problem is, it's a biased sample I'm getting. The sample I'm getting is, if the local detector gives you an alert, generally it works. If the local detector doesn't have an alert, there is no knowledge of what it has. In the previous setting, I knew that it was less than 0, and it did not report. But now, I have a third condition. I knew that maybe there is nobody there, and that's why nobody reported. Or, you see, that changes the picture completely. It could be that I got 95 alerts from 10,000 nodes, in which case it's clearly all just random noise. It's the tail of the -1 Gaussians. Or it could be 95 alerts out of 100, which means that it's strongly it's a malware in the system. And you can't distinguish between those two. But by playing one small trick, you can indeed solve this problem. The trick is the following. You ask each person who reported the alert to give, along with the alert, the signal that generated that. Then what do you see? You basically see two conditional distributions of this type. Okay? If it was all false positives, okay, then you will see the conditional distribution of the signal, given that an alert occurred, to be this. It's the tail of a Gaussian of -1, 1, condition that is greater than 0. On the other hand, if it was all the malware, you'll see the tail of a Gaussian 1, 1, condition is greater than 0. So now you can run a KL divergence test on those. You can't do count, but you can do a KL on the alert measure, on the alert signal, and figure things out. Okay. So this makes it robust to size variations. Okay. So now, okay. So this is what we call discriminating to shape of the alerts. Okay. There's one more thing we need to add. So what did we do? So going back to our setting, we did shape, which is this trick, along with count. So which is filtering based on neighborhoods and communities. So you need to do adaptive filtering. So what does it mean? If you see an alert, you will report it along with your feature vector, if and only if a one-hop neighborhood of u within some pre-specified interval of time also shows a certain density of alerts. Okay. Essentially. And then we take those biased feature vectors, that's basically what we have, and compare conditional distributions, okay, of baseline. So it turns out that the conditional distributions separate really strongly. So this is the, okay, so conditional distributions itself is a very high dimensional object right now. It's a 10-dimensional object. So what we did is we compared the Wasserstein distance, which is some other surrogate of, it's not KL, it's some other distance metric. I'm happy to talk about it offline. We compare, for each time you get a signal, you compare its distance with some baseline, say uniform distribution. Once you have that, that gives you something, that's now we get a scalar metric, and then we plotted that distance over many realizations, okay, for benign and for malware. It's a nice sharp separation. It's basically means that at the global level, a threshold test will basically separate these two in this kind of setting. And indeed, for many scenarios, this false positive, true positive, you can boost it up much, much better by using this kind of correlation. So this is where we are at, using distribution shape plus censoring. It doesn't work all the time. These are good examples. Sometimes these things overlap, in which case you get error probabilities in one ad. So this is for 7 of the ads, it works very well. For a couple of them, the data shows it's really miserable. In one, it as good as random guessing. Okay, but this is still work in progress. So this is where we are at. So the point is that network effects tells you how to track where to look and when to look, and that can essentially boost signals quite a bit. And we are trying to build it in one context. So that's there. Thank you.